The Navy announces that Wake Island is probably captured by the enemy. And now it is disclosed that fewer than 400 Marines held Wake Island for at least 14 days against heavy Japanese attacks. The Marines had 12 fighter planes and a small quantity of weapons.
Good day, and welcome back to Mike's Radio Repair and Restoration. In this video, we're going to cover some basic receiver theory. If you might have noticed, if you watched my four-part series on restoring a Helicopter S-38, I kind of glazed over oscillator coil and antenna coil alignment, as I kind of sort of felt the new folks out there really need to understand how a receiver operates before you can really get into the meat and potatoes. And it's not hard, and we're going to go through it. So one of the things that I find important is I've started a Facebook page, again, called Mike's Radio Repair and Restoration. All the new folks and folks with experience alike should please join the page. The idea is putting together a community of people of just starting out or people with experience, and to be able to help each other and talk about problems and pass schematics back and forth. I think it'd be a great community to build, so consider joining that. Certainly, there's going to be more learning opportunities in there, and some of the people who are long in the tooth and know the stuff already can come and help out the new folks. Any more people we can get into the hobby who are curating and restoring and repairing these old radios, the better. Rather than they end up in the dumpster. Because, after all my years of being in this hobby, I'm still finding radios in basements and attics and garages that are completely worthy of restoring. So we're going to start off a little simple. Some of you folks may know this stuff already. Some of you may not. And for those folks who are in the knowledge of the stuff, the first part may bore the pants off you. But I hope to be able to get through it and take a novice who is brand new to this and is still grappling to understand what's going on right from the get-go, and try to help him or her understand what's going on. So I prepared this in segments or slides or modules, if you will, to start from the beginning, and I'll try to pace through them fairly quickly, and I will try to keep the language straightforward and simple. So with that, let's begin with our first module. Okay, we're looking at an atom of copper, and this is what most electrical wires are made out of, or at least this is good for understanding. And as we remember from high school science, that an atom is comprised of protons, neutrons, and electrons, and usually, not in every case, but in most cases, electrons or protons and electrons balance. Now, this being a copper molecule, it has one outside electron, and it's called a valence electron. And the special thing about copper is, and this is the difference between conductive and non-conductive material, copper will accept another valence electron for 2, so it throws it out of balance for a period of time, as where a non-conductive atom will not accept that another valence electron. So that's pretty straightforward. We're just going to go to the next module here. And I don't know how well you can see this. It didn't turn out very well. But this is a string of copper atoms. And imagine it as a wire. So if in the end here, my electrical source, a generator, a battery, AC, DC, whatever you want, if I add a second electron to the outer valence of this copper atom, it will accept it. And if I add yet again another, making a 3 total, well, this atom becomes very unhappy and it wants to eject one of those electrons right away. So that's what it does. It passes that extra electron to the next atom. And if I add another one to create third again, it will again pass it off. And that's how this works, is that electron will flow through a wire by like a old-fashioned fire bucket brigade. So the outer balance will accept electrons to a certain point before it becomes unhappy, unstable, and passes an electron on to the next one. So that's how electricity flows, for those folks who didn't know that. So here we have pictorials, or a graphical representation of AC and DC. And if you don't know what that is, we have a scale here. We have voltage starting at 0 in the center, positive going up, negative going down, same on the side. And this is over time. So if we think back to our electron flow in a wire, in direct current, the electrons are always flowing in one direction, always in the same direction, and that's DC, that's direct current. And this is AC. We have a varying voltage that starts at 0, climbs up on the positive, comes back to 0, then climbs down on the negative. Then the cycle continues, repeats itself. So the electricity is actually vibrating back and forth, if you will, in the wire. So that is an alternating type of a current. Here we have a transformer, and it has two coils in it, a primary and a secondary. And mostly we use transformers for, in the lower frequency range, or AC, for stepping up or stepping down voltages, or we use it for filtering RF at higher frequencies. But let's look at how a transformer works first. A transformer works by what's called mutual inductance. And here we have a primary coil and a secondary coil. So if we feed voltage in, as shown in this chart here, an AC voltage, to a peak, magnetic lines of force develop around the primary coil. And at this peak, this pole may be north and this one may be south, just like a magnet. And when this waveform drops back to 0, the magnetic lines of force collapse. And when it drops down below into the negative range, that lines of force recreate again, but the poles change. This may be south and that may be north. So as the cycle progresses, this magnetic field is collapsing and expanding in time with this wave. Now, what happens to the secondary coil when these lines of force cross this coil? They induce the flow of electrons, like we saw in the electrical copper wire where we do the bucket brigade thing. So we can have energy cross into the second coil by way of induction. So these lines of force give the electrons a little kick in the secondary coil. And this is really very a mathematical, easy to calculate type of ordeal. If you have, let's say you have 100 turns on the primary and you're putting in 100 volts AC, and you have only 50 turns on the secondary, if you're putting in 100, you're going to get 50 volts out. It's just that simple and that easy to calculate. With RF, it's a little different. We have to look at what we call a tuning or a tank circuit. So here we go. This is a tank circuit. This is got 3 factors in it. It has a coil, which is known as an inductance, We have a capacitor, and we also have, although it's not shown here, but it is in the wire, resistance. So we have R for resistance, L for inductance, and C for capacitance. Depending upon the specifications, or the size of the capacitor, or how many microhenries the coil is, will determine what this tank circuit will oscillate at. And that's what this whole tank circuit does, is designed to oscillate at a given frequency. And that frequency is changed by changing the values of the inductor, capacitor, or resistance. So often you'll come across a schematic diagram with an inductor or a coil or a capacitor with a line drawn through it like this. that means that you can tune these, that you can change, increase or decrease the inductance, or increase and decrease the capacitance. Because, I mean, you may go and do all the math and complete the calculation, say, I need this much resistance, this much inductance, and that much capacitance. But when it comes to play, you know, there's other things in the chassis metal and the tubed input and all kinds of things that can impact where this resonates, what frequency this operates at. So you can adjust these things to bring this tank circuit onto its designed value. And this is part of oscillator and antenna coil front end alignment, is adjusting coils and capacitors to bring them into the proper specification. So with that in hand, we have a block diagram of a basic receiver. I'm just going to very quickly go through the blocks here, and we're going to get into the nitty-gritty detail of it. But we have our antenna, and we have a filter. Because, I mean, when we want to turn on a receiver, we want to receive a given station. We don't want to receive everything all at once, so we have to have a reasonable amount of filtering to start with. We have a magical device that we're going to get into in the next segment here called a mixer. And this variable frequency oscillator is actually your tuning dial. And then we have what is called an intermediate frequency, because our mixer is going to convert, do some converting to a common frequency. Like most radios, these old tube girls have an IF of 455 kilohertz. So we can have a lot of processing and filtering in the IF amp. But it goes into detection where the signal is converted from RF back into audio and an amplifier. And that's a very simplistic view of how this radio works. And for the function of this module, we're going to be focusing on the S38 that we did a full restore on, because it's a simple heterodyne receiver. And that's what this here is now. This was a great invention. It was originally patented by a guy named Edwin Howard Armstrong, but I think a French guy actually beat him to the patent later on. But this is how they created a heterodyne. This is a heterodyne receiver, not a super heterodyne receiver, but just a heterodyne receiver. Okay, this is the core of a heterodyne receiver and a mixer. A mixer is a great device that takes two frequencies and mixes them together and produces different frequencies. The output of the mixer is always the sum and the difference of the inputs. And here we have two inputs. We have a radio station in the AM broadcasting on 1450 kilohertz. We have a VFO, which is a variable frequency oscillator, which is your tuning knob, which is attached to a small oscillator that generates a small signal RF. And it runs at 1905 kilohertz. And when you have this tuned to 1905, we're going to receive 1450. The mixer is going to put out two signals. It's going to put out a signal on 455 kilohertz, and it's going to put out a signal on 3355 kilohertz as well. So the math here is very simple. The sum, is frequency in 1 plus frequency in 2 equals frequency output. And the difference is very simple. Frequency in 1 minus frequency in 2 equals frequency output. So the beauty of this is you're converting all of the radio signals coming into the radio to this is the chosen frequency that most of these old girls run at. The IF runs at 455 kilohertz. Now the benefit of that is, and we'll look at the schematic in a little bit, is to tune at 29 megahertz versus 1 megahertz requires a completely different set of coils and capacitors. So if you wanted to have a receiver that goes from the bottom of the AM broadcast band to like 475 kilohertz all the way up to 30 megahertz, your radio would be the size of a tank and full of coils and capacitors, and it would be very inefficient. The real benefit of this is you're now converting everything to the same frequency for processing. So now at 455 kilohertz, I can significantly amplify and filter this frequency and feed it into the detector and then into an audio amplifier and process radio. Very simple. So let's look at another example here. We have a radio station at 1260 kilohertz, and we have our VFO injecting at 1715 kilohertz. And again, we can reach our 455 kilohertz destination frequency, and the sum of 2975 kilohertz is there. Now, this is what I call high side injection, to where the VFO is always tuned 455 kilohertz above the desired receive frequency. It's not always this way. We're going to get into that in the next slide, but that's how this particular slide works. An important thing to remember, and this is not written in the S38 instruction manual anywhere, the first 3 bands are high side injection, is to where band 1, band 2, and band 3, the VFO is always running above 455 kilohertz above the desired frequency. As you can see, that's what's happening here. So you can have a VFO that's so poorly tuned or mistuned, or you've done service work on it and it's changed radically. You know, so I mean, here's basically how a tuning is going to work on the S38. You're going to set your signal generator at 1260. You're going to set your dial at 1260, and you're going to tune the inside capacitors and inductors until you reach this frequency here. And you can actually, to make sure that you hit 1715, you can take an external shortwave receiver and tune it to 715 and listen for the signal. Like if you have another receiver on your bench, you can cheat rather than using a spectrum analyzer or other tools. You can actually cheat, and we'll get into how we can do that a little later on. But this is high side. We'll get into low side next. And here we have a radio station at 30 megahertz, and here we're 455 kilohertz below the desired frequency. So, but again, you can reach the difference of 455 kilohertz for processing. So this is kind of sort of the deepest theory you're going to run into, not necessarily theory, but the deepest portion operation of a radio is how this mixer works. I hope you take the time to go back over these slides and understand this fully. If you have questions, you can post them here on YouTube, or better yet, join our Facebook group and post them over there. There's no such thing as a stupid question, because I mean, I'm not the greatest teacher in the world, but I sure would like to help some folks along. So this is low side injection, as to where our VFO, or a variable frequency oscillator, is injecting into the mixer 455 kilohertz below our desired frequency to get our desired output. So we go back to this slide here now, and we have our antenna, we have a filter, we now know how this mixer works, so we tune our VFO so that all of the desired frequencies are all mixed to 455 kilohertz, where we can process and amplify them in much greater detail than we can if we didn't have this type of an arrangement. And of course, then we have our detector, which converts RF, radio frequency, back into audio, and a simple audio amp to bring it up so you can hear it. We're going to take a little tour of the S38 chassis here to take some of this knowledge that we've kind of sort of learned and learn how to identify it in the radio. So the first thing I'd like you to notice is here we have a dual ganged capacitor. It's a variable capacitor. You can see that the plates come and go and increase and decrease the amount of capacitance. And there are two. They are separate. They do two separate things, and we're going to get into that. And also on the fine tuning, or the band spread side, we can see there's a much smaller capacitor here. And again, there's two. And they both do very separate things. And you can see we have two. These are the intermediate frequency transformers that we're going to get into. So now we're going to just flip this old girl over. Okay, so we have, now the S38 doesn't have tunable coils, but what it does have, well, sorry, incorrect. The S38 doesn't have tunable inductors. It uses tuning capacitors to be able to set it. So the VFO oscillator is there's a set of coils underneath each of these capacitors here. So you can adjust where the VFO oscillates for each band. And that's what we've got here. We've got a coil and a capacitor for each band. And simplistically, the idea is to make the dial accurate. So if I put the dial on 1500 kilohertz, I can adjust the oscillator until the radio is receiving 1500 kilohertz. And then we have another set of coils over here as well. And this is the receive coils. This is the filter on the input that we showed on our block diagram. And again, we can tune these coils to accept the band we want and reject others. So that is pretty straightforward there. Now, when it comes to tuning this, if you're curious, download the schematic. The manufacturer's instructions for alignment on this radio are pretty clear. And once you look at them and read them, you'll begin to understand, okay, what has to happen here, how we're calibrating the dial. So now we've kind of sort of seen some of the stuff we've been talking about. So let's start looking at schematics now. Okay, we're looking at the front end, if you will, of the S38. This tube here is the mixer tube. We have a set of switches here. This is all ganged onto one switch, and it is the band switch. And you'll notice up here, this is the antenna input. So the antenna signal comes in here. Now you'll see a bunch of coils and capacitors. This is the antenna coil we identified under the chassis. So when you change to a given band, it'll switch in the appropriate coil that allows that band to pass, like band 1 or band 2 or whatever the case may be. Now, when you change to band 1, this happens down here. Now, this is the oscillator. Again, we have trimmer capacitors here that allow us to adjust the frequency of which all of these oscillate, so that when I have this, when this is all set on band 1, let's say the broadcast band, I've tuned my antenna coil using my signal generator and following the manufacturer's instructions for best signal through. And down here, I've tuned the proper capacitor based on manufacturer's instructions to give me the right injection point based on what the dial says. If I've got the dial set at 1600 kilohertz, then we know that our oscillator is going to run at 455 kilohertz above that. So you can track it with another radio, or you can just simply tune the capacitor for band 1 until you receive the best signal on 1600 kilohertz. This is not hard stuff. So then you'll go on to band 2 and you'll do similar. You just follow the manufacturer's alignment instructions to tune the input coils from the antennas and to tune the oscillator coil for the mixer. Okay, I'm just going to sneak this piece in here because I forgot it, and it's kind of an important step here. We were going through the antenna coils and the tuning of them. What I didn't include an explanation for is these tuning capacitors shown here with the lines connecting them. These are the two tuning gangs that I showed you on the top of the S38 receiver. One is a coarse tune and the other is fine tune or band spread. But they are tied together. So when you move your VFO knob, which is that dual capacitor, both the antenna coils and oscillator coils move in unison. So your receive frequency coil is peaked up as you go. Same with the VFO coil. The frequency changes according to what's on the dial, the way you've done dial calibration. Not the greatest explanation, but nevertheless, here they are. They are tied together, fine and coarse tuning, as you saw on the top of the S38. so that the antenna coil and the oscillator move in unison. Okay, just to say this in a different way, in regards to these tuning capacitors that we showed you on the top of the set, I said there was two distinct different ones, and we have the main tuning capacitor, and we have the fine tuning, which is noted as band spread, and we have it over here too. So these are the two units I showed you on top, and they move together. The capacitor, as you tune, the two capacitors move together, and they keep synchronicity between the antenna coils and the oscillator coils. So as you tune, the oscillator changes frequency via that capacitor, and the antenna input coil also changes frequency to match. So there's synchronicity between these two. I think that probably better explains that. Now, just we can see this on this schematic here. This is the output of the mixer, and of course we can see that is the input of the mixer for the antenna, and we've got the input of the mixer here for the oscillator. So signals are combined in the mixer here, and the output is here, and it goes into a transformer. At the output here, we know we want 455 kilohertz, and that's exactly what these two transformers here are tuned for. We tune them for 455 kilohertz for maximum pass of 455 and rejection of everything else. So let's look at the rest of the receiver in the next slide. Okay, so now we understand how the front part of the receiver works. We understand how the oscillator works. We understand both signals are presented to the mixer, and the mixer out tunes everything to 455 kilohertz. And we know that this transformer here, which is adjustable, which you would have watched in my series of videos of restoring the S38, how to tune these. This transformer is tuned to 455 kilohertz, and the output of it is here. It heads into an IF amplifier. This amplifier is set up for 455 kilohertz, and it greatly amplifies the signal. And once again, it's passed through another transformer, which again just allows the passage of 455 kilohertz and rejects the rest, and it gets fed into the detector. This detector is quite simply turning RF back into audio, and then the audio is passed on to the final audio tube here. So that's pretty straightforward. And down here, we've gone through the power supply. We've got the rectifier tube, which turns AC into DC. And this is a kind of sort of an unusual unit, being an AC-DC unit, not having a transformer. And we've got our speaker output transformer here, our output audio transformer, and our speaker. So we're not going to get into the gross details of how this all exact operates, because I really want you to understand in a block way how this all works. So hopefully you've managed to follow along. So there you have it, a basic look at receiver theory. I do encourage questions, and like I said, I do encourage you to join the Facebook group. I can better answer your questions with schematics and images and links over there, so please join the Facebook group. Like and subscribe for this for sure. We can certainly stand to build a bigger, better community here. So at this point, I hope this was helpful. We're going to be doing a secondary part of receiver theory where we get a little bit deeper into it. We're going to get into images, and we're going to get into, this was just a heterodyne single conversion receiver. We're going to get into super heterodyne receivers, which is dual conversion, which take care of a lot of image problems, but we'll get into those deeper things as we go. So I hope you enjoyed the video. Again, let's get all the questions out. Let's get everybody on board understanding this. Heterodyne receiver is certainly a remarkable invention for being able to take all of the frequency out there and converting it down to a common frequency for processing. You get a tremendous gain in doing that, being able to process all one frequency rather than having to process them all. So until the next video, thanks again very much, folks, for tuning in, and we look forward to seeing you again.
The Marines had 12 fighter planes and a small quantity of weapons. They were commanded by a 38-year-old Marine Major, James P.S. Devereux. They sank 1 Japanese light cruiser and 3 destroyers. They held out against 13 raids.